the 15th of August, 1977. A quiet control room in Ohio. A printer rattles out a thin strip of numbers and letters. 6EQUJ5, like a heartbeat from the sky. A volunteer circles it in red ink and writes a single word. Wow. In that moment, the universe feels less like empty space and more like a place that can answer back. What made that 72-second whisper? It landed almost exactly on the most famous frequency in radio astronomy, the one set by neutral hydrogen, the atom that stitches the cosmos together. Not a messy roar, not the wide hiss of natural noise, a narrow, clean spike. The kind of tone you would choose if you wanted to be heard across light years. But then, silence. Minutes later, the telescope's second feed slid across the same sky and heard nothing. For days, months, years, teams went back with sharper ears and wider nets. Nothing. No echo, no repeat. Just one perfect rise and fall that matched the way the Earth's rotation carries a source through a fixed radio beam, as if a lighthouse swept past us once and never again. Was it a comet's cloud briefly singing at the hydrogen line? A flare ricocheting through cold gas? A stray reflection of our own technology? Or was it what so many quietly hoped for, a deliberate signal, aimed or accidental, that tagged our planet and moved on? Today, we listen with instruments 1,000 times more capable, giant dishes, supercomputers, arrays that peel the sky into billions of channels. We can replay, triangulate, and compare in real time. And yet the most famous message we ever received remains a question mark scribbled in the margin. This is the story of that minute, where it came from, why it never came back, and how a single red ink exclamation turned a quirky anomaly into a disciplined search for company in the dark. If the universe meant to say hello, this is where we first learned to say, "We're listening." Picture the instrument that heard it. Big Ear wasn't a dish that slewed like a camera. It was a giant, immovable ear made of aluminum panels, split into two listening feeds called horns. The sky did the moving. As Earth turned, a narrow slice of space slid through the beam, rose to a peak, and drifted out again. That sweep takes roughly 72 seconds for a point-like source long enough to watch a clean rise and fall, too short to get a second chance if the source is fleeting. This geometry explains the wow signal's most haunting feature. The first horn heard a narrow, bright tone that climbed and faded exactly the way a steady transmitter should in a drift scan. A few minutes later, the second horn scanned the same patch of sky and heard nothing. One horn, one pass, 1 minute. If you wanted a recipe for a mystery, you'd write it like that. Those 6 characters, 6EQUJ5, are not a code from space. They're a compact way Big Ear's computer printed intensity. Weak values showed up as numbers, stronger ones as letters. The letter run in the middle, EQUJ, means the signal rose far above the background before dying away. The crucial part isn't the typography, it's the shape. Narrow in frequency, smooth in time. Nature can make noise that's loud. Nature can make bursts that are brief. But nature rarely makes something this clean and needle-thin right on a famous frequency. That frequency matters. Neutral hydrogen naturally emits at about 1.42 gigahertz. Because hydrogen is everywhere, that line is the best-known landmark on the radio dial. It also sits in a relatively quiet region of Earth's spectrum, the water hole, between the hydrogen and hydroxyl lines where natural backgrounds are lower and many searches concentrate. If you were building a cosmic beacon, this is where you'd put it. If you were searching for one, this is where you'd listen longest. Why didn't the second horn hear it? The simplest answer is geometry. The two beams were offset on the sky. A source sitting between them could pass through one beam and miss the other. Another possibility is timing. A transmitter that turned off, rotated, or swept past could be gone by the time the second beam arrived. There's also the unromantic answer: interference. A reflection from an aircraft skin or a satellite panel can mimic a narrow tone and vanish just as quickly. In the 1972nd, with far fewer satellites, that possibility was smaller, but not zero. The way Big Ear observed complicates the autopsy. It did not record raw voltages we could replay. It printed summaries. That means we can't recover phase, measure Doppler drift precisely, or split the tone into finer channels after the fact. We have a strip of characters and a diagram of where the beams were. That's both the charm and the frustration. The night is documented, but not in the forensic detail modern instruments capture by default. Even with those limits, the data say several firm things. First, the signal was narrowband, a hallmark of technology. Second, the time profile fits a drift scan through a steady beam. Third, it landed very close to the hydrogen line, the universal frequency technosignature theorists have recommended since the early days. Fourth, it never repeated in later campaigns, even with better receivers. Taken together, those facts keep the WOW signal in the small, stubborn set of anomalies that resist easy explanations. Let's unpack the interference question. A transmitter on or near Earth usually betrays itself by moving with us. Towers stay fixed, satellites follow orbits. Our planets spin and orbit imprint familiar Doppler patterns. Their signals often smear across multiple frequencies or drift in ways that match our motion. The WOW printout doesn't preserve enough detail for a rigorous Doppler test, but its tidy, symmetrical rise and fall match a source that stayed put on the sky while we rotated under it. That argues against a local transmitter, though it cannot rule one out. Now, the other side. Could nature do it? A few mechanisms have been suggested. A pocket of hydrogen gas can amplify radiation under the right conditions, briefly stimulating emission on the line. A violent radio flare smashing into a cold cloud could sharpen and brighten the tone for a moment. Ionospheric or interstellar lensing could, in principle, focus a broader signal into something that looks thin. Each idea explains one piece, the brightness, the thinness, or the brevity, but none fits all three comfortably at once. There's also the small but tantalizing detail that the candidate's sky position sits in Sagittarius, a rich, crowded backdrop near the plane of our galaxy. In that direction lie hydrogen clouds, star-forming regions, and ordinary stars where a technological civilization could reside. Modern catalogs list sun-like stars near the candidate coordinates. That proves nothing, but it does give teams obvious targets to recheck with better ears. The last ingredient is humility about the instrument. Big Ear was brilliant but idiosyncratic. Its twin horn layout created two plausible positions for the source. Its data system compressed rich waveforms into alphanumeric shorthand. Its environment on a college field beneath busy air routes was not immune to stray reflections. When the telescope was dismantled, the chance to rerun the exact setup died with it. Any verdict we deliver has to live with those unfixable uncertainties. The fair reading is this: the instrument and the geometry make a single, narrow, clean tone right where a technosignature might live, look very much like a real, on-sky source that passed through one beam and not the other. That is unlikely enough and important enough to justify the next steps translate that cryptic 6 EQUJ5 into a physical brightness, connect brightness to distance and transmitter power, and test natural and artificial pictures against the numbers. Imagine turning that red ink scribble into physics. The strip says 6 EQUJ5, but a radio astronomer reads it as a narrow tone rose far above the noise, peaked, and faded over about 72 seconds the time it takes the sky to drift through a fixed beam. The letters aren't a cipher from another world. They're a compact way the Big Ear computer binned intensity. Numbers marked weak levels, letters marked stronger ones. In plain terms, the WOW tone wasn't just detectable, It was impressively bright compared to the background, and almost all of its power sat inside a sliver of frequencies rather than smeared out like natural static. To translate bright into something you can compare, astronomers talk in flux density power per square meter per hertz measured in Janskys. 1 Jansky is absurdly small, a 10 octillionth of a watt per square meter per hertz, which is the kind of whisper you get from stars and galaxies at radio wavelengths. Big Ear didn't print 15 Janskys or 200 Janskys, it printed those alphanumeric bins. But the pattern letters high in the sequence tells you the spike rose well above the ordinary hiss of the receiver. In modern language, the signal-to-noise ratio was strong enough that nobody would mistake it for a random fluctuation. There's a second clue hiding in the timing. Big Ear's beam was like a flashlight glued to the ground. The Earth's rotation carried the sky through it. A steady source drifts in, brightens, and drifts out with a smooth, symmetric shape. That's exactly what the wow trace did in the horn that heard it. If you sweep a tuning fork across a microphone, the loudness curve looks the same every time. The wow curve had that tidy tuning fork symmetry. Now, why does narrowband matter so much? Natural processes love to sprawl across frequencies. Thermal noise from warm gas is broad. Lightning-like bursts from magnetic explosions can be spiky in time, but they usually spread out in frequency. A narrow tone a few hertz, a few tens or hundreds at most is what a crystal-stable oscillator makes. Engineers know how to do that. Nature can, in special cases, but it takes contrived conditions. That's why the hydrogen line neighborhood around 1.42 gigahertz has long been called the water hole, the quiet lane where a technological beacon would stand out against the background. From "we saw a spike" to "how powerful was the transmitter," you need a bridge. The bridge is the radiometer equation, which tells you how bright a signal must be to rise above the noise of a receiver with a given collecting area and temperature in a given integration time. You also need the telescope's effective area, how big an ear it really has for that wavelength and the channel width that caught the tone. Big Ear's back end carved the spectrum into narrow channels, and the spike sat in or across one of them, which is exactly what narrowband means in practice. Once you have an estimated flux at Earth, you can play a thought experiment. Imagine the transmitter isn't trying to be subtle. It's broadcasting more or less isotropically, like a light bulb. Then the power you need climbs as the square of the distance. A modest beacon that would be trivial to hear from across our own solar system would be punishingly dim from even the nearest stars. That's why technosignature studies rarely assume isotropic power. It's wasteful. Beaming is the trick. If, instead, the source uses a high-gain antenna dish focusing its energy into a tight, sweeping beam, the required transmitter power is much smaller for the same received flux. That's how our own deep space networks talk to interplanetary probes with kilowatts rather than terawatts. Swap in a large, steerable dish on the transmitter's side, and a wow-level tone could plausibly come from a civilization using power levels well within modern human capabilities, provided the beam happened to sweep across Earth for a minute. This sets up two contrasting pictures. In the near and modest picture, a transmitter on or near a nearby startons of light years away could be using power in the range of human technology if it beams tightly. In the far and formidable picture, a transmitter hundreds or thousands of light years away could still be heard if its beam is extremely narrow or its power budget is enormous. Both are physically possible. The drift scan shape doesn't tell us which one we saw. It only says the source sat fixed on the sky while we rotated under it. There's another wrinkle: Doppler drift. Any narrow tone sent from a rotating planet, orbiting star, or spinning spacecraft will creep up or down in frequency as their motions add tiny pushes and pulls. Modern searches look for that drift explicitly by de-chirping candidates, signals testing a range of tiny slopes to see where a spike snaps into focus. Big Ear's analog era backend didn't archive raw voltages, so we can't rewind the tape and measure the drift after the fact. If a subtle Doppler slope was present, it was effectively baked into the printed bins. That's frustrating, because a well-measured drift rate would have given us an immediate clue about whether the source felt like local hardware or distant transmitter. Beam shape matters, too. Big Ear had two slightly offset feeds. Think of them as two parallel lanes on the sky. The same point on the sky would pass through both lanes with a short gap between them. A point source right down the center of one lane might miss the other entirely. A source slightly off could brush both. The WOW event showed up in exactly one lane. Geometry alone can do that. But geometry can't explain why nothing ever reappeared in either lane during the many revisits that followed with other telescopes. That one-and-done behavior is the heart of the mystery. Could an earthly transmission have bounced off something high above us and masqueraded as a cosmic tone? In principle, yes. Metallic skins aircraft, satellites, even spent rocket body scan reflect and momentarily focus radio energy like a moving mirror. The 1970 sky had far fewer reflectors than today, but it wasn't empty. The strongest argument against a reflection is the way the signal rose and fell with the exact profile you'd expect from a source fixed on the sky, not moving with us. The strongest argument for caution is that the instrumentation didn't record enough forensic detail to eliminate clever interference with absolute certainty. What about natural astrophysics? There are niche mechanisms that can make the hydrogen line sing. Under particular densities and temperatures, hydrogen gas can experience population inversions conditions that act like a radio laser and narrow the emission. A blast wave or flare crashing into a cold cloud might briefly sharpen and brighten the line. Interstellar scintillation twinkling, caused by turbulent plasmacan focus and defocus radio waves, momentarily boosting a background tone into visibility. Each of these buys you one feature: narrowness, brightness, or brevity. Getting all three on the nose at the right time and place is the hard part. That's why no single natural theory has won the day. So what does the printout really give us? 4 sturdy pillars. First, narrowband. The energy lived in a tiny slice of spectrum. Second, drift scan shape. The time profile matched a source fixed on the celestial sphere. Third, proximity to the hydrogen line. Not proof of intention, but the most conspicuous address on the radio dial. Fourth, non-repetition. Despite many rechecks, nobody has caught the same tone from the same spot again. Those pillars don't build a verdict. They build a test bench. On that bench, we can now place hypotheses and ask what power, what beam, what distance they imply. A beamed artificial transmitter, it has to explain the single-pass detection and the silence afterward. A natural hydrogen line flare, it has to reproduce the narrowness and the clean drift profile. A terrestrial reflection, it has to mimic a celestial drift and land exactly on the most famous line in radio astronomy. In the next section, we'll stress test each picture with simple, order-of-magnitude math, not to force a winner, but to see which ones refuse to break. Let's put numbers on the stories we keep telling. The printout shows a narrow band spike, well above the noise, about 72 seconds long, near the hydrogen line. A telescope with about 1,000 square meters of effective area and a few hundred Kelvin of system temperature will easily detect such a tone at tens of Janskys. That aligns with a bright, clean spike, not a messy broadband burst. Now turn flux into transmitter demands. 1 Jansky is 26 watts per square meter per hertz. The flux at Earth equals the sender's effective isotropic radiated power EIRP divided by 4 pi r2 and by the signal's bandwidth. For a 1 Hz tone from 100 light-years away, a tens of Janskys detection implies an EIRP of roughly 13 watts. That sounds absurd until you remember EIRP includes antenna gain. Give the sender a high-gain dish, and the actual transmitter power is lower by that gain factor. How much lower? A stadium-scale reflector at 1.42 GHz can have linear gain near 10^7. With that, the physical transmitter power needed to reach 10-13 watts, EIRP, is under a megawatt. Large, but within human engineering or planetary radars paired megawatt transmitters with huge gains to achieve multi-terawatt EIRPs, push the distance to 1,000 light-years and scale by 100. Now you want tens of megawatts. Ambitious, but still engineering. Flip to the isotropic case. Remove gain and a 100 light-year beacon must pour 10-13 watts into a single hertz in all directions to match a wow-like flux. That is wasteful to the point of nonsense. If the wow signal was artificial, it almost certainly rode on a beamond. A beam naturally explains one pass. A narrow lighthouse swept Earth once and never again. On feasibility, a beamed artificial origin holds up. Sensible energy. The drift, scan shape expected from a steady source in Big Ear's geometry, a rational hailing channel, and non-repetition consistent with a rotating or scanning beam that missed us later. Two measurements would test or break itones we do not have, a Doppler drift encoding the sender's motions, and a repeat that fixes period, orbit, or precise sky position. Nature next. Could neutral hydrogen briefly sing at exactly the right frequency, narrow and bright? In special conditions, yes. Population inversions can turn gas into a maser, narrowing and boosting emission. But hydrogen masers rarely sit exactly on the 1.42 GHz line, and when hydrogen does flare, it is usually broader than a hertz or two. You can sharpen emission with low temperatures and gentle velocity fields, but that already feels tuned. A flare slamming into a cold cloud is another idea. A shock can pump a thin slab and momentarily stimulate emission on the line. Brevity is easy. Brightness can be arranged. Narrowness is the sticking point. Thermal motions, turbulence, and magnetic fields smear frequency. Packing most power into a razor-thin slice asks for a calm, cold, well-ordered column and a lucky viewing angle. Terrestrial reflection? Picture a transmitter near 1.42 GHz bouncing off a moving reflector, an aircraft fuselage, a satellite panel, a spent rocket body. The reflected tone would be narrowband by inheritance and brief by geometry. The challenge is the time profile. Local sources carry the stamp of our motion. Sloping frequency drifts from Earth's spin and the reflector's path. Big Ear did not archive raw voltages, so we cannot refit a drift. Even so, the single horn trace had the clean, symmetric rise and fall you expect from a source fixed on the sky while Earth's rotation sweeps the beam across it. That weighs against a nearby gadget even if it cannot rule one out. Scoreboard, beamed artificial passes, energy and timing, sits naturally on the waterhole, explains one pass, but wants Doppler and a repeat. Isotropic artificial fails the energy budget by orders of magnitude. Natural hydrogen line flare can be bright and brief, struggles to be razor narrow without special pleating. Local reflection fits brevity and narrowness, struggles with the celestial drift profile. One more envelope check. Suppose the peak flux density was about 30 Janskis in a hertz. At 100 light years, an Arecibo-class beam transmitter needs well under a megawatt. At 500 light years, a few megawatts. At 1,000, several tens. All are big but boring for an industrial civilization. Non-repetition remains the hardest fact. A periodic lighthouse should come around again unless the duty cycle is extremely low, the period is long, or the beam is so needle-thin that our line of sight aligns only once in decades. A one-time broadcast explains silence, but it is a strange strategy for any communicator who wants to be found. Natural and local ideas handle only once more easily. yet struggle with narrow and clean on the most conspicuous frequency in radio astronomy. So the math does not deliver a verdict. It delivers a posture. Treat beamed artificial emission as feasible and worth targeting. Treat isotropic beacons as fairy tales. Treat hydrogen line fireworks as rare possibilities that demand follow-ups capturing raw voltages and Doppler drifts the instant a candidate appears. Treat reflections as the null every pipeline must kill first with on-off beam switching, multi-site checks, and rapid cross-observations. That posture is what modern searches adopt. Next, we zoom out to equipment, arrays that can look on and off target at once, backends that split the dial into billions of channels, and software that can ping other telescopes in seconds. When the next wow rises from the noise, we should not get a strip of characters. We should get a movie of the signal's life, from first whisper to last fade with enough detail to argue less and measure more. If the wow signal happened tonight, we wouldn't get a cryptic string on thermal paper. We'd get a live movie. A waterfall plot would bloom in real-time frequency vertical, time horizontal while software froze raw voltages in a rolling buffer so nothing is lost. Next to it, multiple beams would show the on-target field and nearby off-targets, letting us ask within seconds, is the spike only where we're pointing, or is it everywhere? Modern instruments make that possible with two upgrades, bigger ears and smarter backends. Large single dishes scoop up faint signals, and multi-dish arrays synthesize even larger apertures while steering many beams at once. The real leap is downstream. FPGAs and GPUs slice the spectrum into billions of microchannels with sub-hertz resolution. That is what lets a whisper-thin tone stand out from thermal hiss and radio clutter and lets us prove a spike is real by replaying and measuring instead of guessing. First triage, geometry. Pipelines compare on-source and off-source beams. A real celestial signal appears only in the on-source beam and vanishes in the references. Side lobe checks add a guardrail. If a tone floods many beams equally, it is almost certainly terrestrial leakage. Second triage, motion. A transmitter on a rotating, orbiting world will not be perfectly still in frequency. Its tone will drift. Modern searches actively de-chirp candidates testing thousands of tiny slopes until the spike snaps into focus. That drift rate is a gold mine. Too large or too weird for a geostationary satellite? Too small for an aircraft reflection? Beautifully consistent with a source fixed among the stars while Earth spins below? Big Ear could not do this in 1977. Now it is routine. Third quick test. Polarization. Natural plasmas and man-made antennas imprint distinct signatures. With dual polar feeds, we see whether a candidate is strongly polarized, unpolarized, or changing with time. A steady, narrow tone that keeps the same polarization while crossing the beam is easier to model as distant than as a chaotic reflection nearby. Then comes the hunt for cousins. Software queries the last minutes, hours, and days for the same frequency neighborhood and sky coordinates, and checks satellite catalogs and aviation bands. Some systems even fire a low-latency alert to partner observatories. Please, point now. That phone, a friend's step, is something the WOW observers never had. If a second dish, hundreds or thousands of kilometers away, sees the same tone at the same celestial coordinates, interference drops on the spot. Machine learning handles the tedious parts. Classifiers trained on millions of labeled events spot fingerprints of radar sweeps, spread spectrum links, and oscillator spurs. They do not decide what is alien. They buy humans time by discarding what is obviously ours. What survives gets human eyes within minutes. Analysts who replay voltages, widen or narrow the bandpass, rotate polarization, and ask harder questions. Strategy has broadened. 2. The hydrogen line remains the universal address, but modern campaigns sweep widely on both sides, include hydroxyl lines that bracket the water hole, and check harmonics where engineering convenience might place transmitters. We also run commensal searches. Technosignature pipelines piggyback on everyday astronomy, so the sky is effectively under surveillance all the time. That is how you catch a surprise, by never stopping. What would closing the case look like today? First, simultaneous detection in multiple on-source beams and at multiple sites. Second, a measured Doppler drift consistent with a source outside Earth's environment. Third, repeatability, either continuous long enough to track or sporadic with an identifiable period. Fourth, coherence across bandwidth. The same tone shows up in adjacent sub-Hertz channels once you fold in the measured drift. Fifth, contextstellar catalogs that say what sits in that beam and how far away it likely is. Why so much rigor when we have seen other dramatic radio events? Fast radio bursts are brilliant, millisecond slashes that repeat from some sources. They once smelled exotic. Now we tie most to highly magnetized neutron stars. Crucially, FRBs are broadband and bursty, not the needle, thin, stable tones that scream transmitter. Another lesson from the WOW era is data permanence. In 1977, the instrument kept summaries. Today, we hoard almost everything. Petabyte archives store baseband captures with timestamps, beam shapes, and calibration states so future analysts can reprocess events with better algorithms. Some projects open those vaults to the public. Citizen scientists trawl spectrograms for anomalies and sometimes find ones the pipelines missed. Even not finding repeats has value, because nulls constrain how often a source could light up without our noticing. There is also a shift in mindset. Rather than waiting only for an intentional hello, many teams look for leakage, the unintentional byproducts of technology, like narrow carriers that power communication systems or clock tones that escape from hardware. Leakage would be weaker than a beacon, but potentially more common. The price is harder interpretation. A faint, drifting tone could be a satellite constellation 50 light years away, or a trick of plasma closer to home. That is why multi-site coincidence and careful drift modeling matter so much. So if a WOW-like spike rose tonight near the hydrogen line, we would interrogate it from every angle in minutes. On, off beams, drift fits, polarization, catalogs, partner dishes. Either it would collapse into the tidy bucket called ours, or it would survive the gauntlet and earn time on the biggest instruments we have. From there, the playbook is simple. Track it, challenge it, and try to make it repeat. The goal is not romance, it is reproducibility. A single minute can inspire a field, but only repeated minutes can change our minds. Next, we return to the sky itself. The candidate coordinates near Sagittarius, the twin positions set by Big Ear's dual horn geometry, and the nearby stars that modern catalogs flag as tempting places to listen again with patience measured in years, not nights. Start with the sky. The WOW detection did not give one dot to point at, it gave two. Big Ear's twin feeds were offset on the sky, like two parallel lanes on a cosmic highway. As Earth turned, the same slice of Sagittarius would drift through one lane, then after a short gap, the other. Because the signal appeared in only one lane, we're left with a fork, two nearly identical right ascensions, two adjacent declinations, separated by the offset between the beams. Both lie in a busy neighborhood close to the Milky Way's plane, rich with gas clouds, young stars, and ordinary suns. In an observatory logbook, those twin positions would be boxed and underlined, Candidate A and Candidate B. Neither is precise to a pinpoint. The beam was broad by modern standards, but they're tight enough to define a target field, a small patch where a narrow tone once stood tall above the noise. If you were planning a reconnaissance tonight, You draw two circles that slightly overlap and start asking what sits inside them. What sits there is not a single celebrity object, but a crowd. The field is sprinkled with faint stars, some cooler than the sun, some warmer. There are hydrogen clouds smudging the background, a few catalogued radio sources whose emission is broad and messy, and a handful of sun-like stars that, on paper, make good technosignature targets. That diversity complicates the story. A natural mechanism could hide among the gas and dust. A technological one would almost certainly live on one of the stars. The dual position ambiguity shaped decades of follow-up. When teams returned to listen, they had to decide, split time evenly between A and B, or bet heavier on one. Early reobservations tried both patches with different bandwidths and channel spacings, sometimes for hours, sometimes for nights. They heard the ordinary radio sky hiss, drifting man-made clutter, cosmic cracklebutt, not the single, symmetric spike that made the WOW printout famous. Modern practice is more methodical. A good campaign begins by mapping the full primary beam with multiple, partially overlapping pointings, so nothing falls in a gap. Arrays go further. They form many simultaneous beams across the field, tiling the candidate zone like a honeycomb. That way, if a narrow tone pops up anywhere inside the WOW footprint, you see exactly which microbeams light up and which stay dark. Geometry turns from a limitation into a diagnostic tool. Catalogs sharpen the hunt. We now carry a phone book of the sky Gaia for precise star positions and motions, surveys that flag stellar temperatures and sizes, mission catalogs listing planets that transit their suns. In the WOW field, you can pick out solar analogs, note their distances, and rank them by how cleanly a radio beam could single out each one. If one of those stars hosts a close-in planet with a measured period, you can time your observations to the planet's orbital phases, just in case a transmitter sits on a rotating world that beams occasionally as it turns. What about the gas and dust in that direction? The raw material for natural explanations. Hydrogen clouds near the plane have their own velocities, temperatures, and turbulence. If a rare inversion or shock-driven flare could sharpen the 1.42 GHz line, that environment is where it would happen. The trouble is, natural line emission tends to be broad and structured, not a needle. So observers use spectral resolution and polarization as filters. Narrow, crystal, stable tones with steady polarization get flagged for special scrutiny. Broad, frayed lines and chaotic polarization go into the natural bin. A practical detail matters for voiceover clarity. Narrowband hunts live and die by frequency stability. To catch a 1 Hz wide tone drifting only a few hertz per minute, your own receiver has to be rock solid. That's easy now. Atomic clocks discipline the backends, and software tracks Earth's spin and orbit, so we can transform the data into the frame of the sky. If a spike reappears near the WOW coordinates, we can measure its drift rate down to a fraction of a hertz per minute and say whether it looks like hardware in space or reflection at home. The dual positions also invite a clever trick. Nodding. Point at candidate A for a few minutes, then nod to a blank patch nearby with similar elevation and azimuth to sample the same terrestrial interference environment. Then nod to candidate B, then to another off-source patch. Repeat that 4-step dance. A persistent celestial tone should appear only when you're on A or B, never on the adjacent blanks. A local nuisance will splatter everywhere or follow the ground geometry rather than the stars. Suppose, on the 5th night of such a campaign, a tone appears not bright enough to make you shout, but unmistakably narrow and steady only when A is in the beam. It drifts gently, the same way, every time you fold the data into the sky's rest frame. You alert a partner observatory a continent away. Minutes later, they see it too. At the same sky coordinates with a drift compatible with a source outside Earth's neighborhood. That is the modern closing move the WoW team lacked. Coincidence across distance, matched drifts, and a shared sky frame. At that point, you are not done but, you are out of the weeds. And if nothing appears, that is not failure. Non-detections roll over into constraints. The field does not host a continuously broadcasting 1 Hz beacon above a given brightness. If a beam sweeps, its duty cycle is below some percentage. If flares happen, they are rarer than your observing cadence can catch. With enough hours across enough seasons, you build a probabilistic cage around what the WoW event could have been, tightening it until only the strangest possibilities remain. The human side of the dual position puzzle is worth saying aloud. Ambiguity is unsatisfying. Storytellers want a single X on a star map. Scientists want a coordinate they can obsess over. The WoW geometry denies both, and that denial is a gift. It forces better strategies, tiling instead of single-point stares, on-off nodding instead of wishful thinking, multi-site coordination instead of one, telescope heroics. The field learned those lessons. The next time a narrow spike rises where hydrogen hums, the response will be practiced, not improvised. So we stand under Sagittarius with 2 modest circles, a crowded stellar backdrop, and equipment finally equal to our curiosity. The plan is simple. Cover both lanes, fold in the catalogs, hunt for a tone that survives every mundane explanation, and if we're lucky, catch it long enough to track. The reward is clarity. Either the WoW field goes quiet forever, and the 1977 spike remains a singular riddle, or the sky coughs up a second whisper, and the mystery finally moves from what if to what is. Let's take the natural explanations seriously, not because they're romantic, but because if any one of them works, it would teach us a new piece of physics hiding in plain sight. Start with the most publicized claim of the last decade: comets. The idea is simple enough to sound right. Comets trail vast clouds of neutral hydrogen. Neutral hydrogen sings at 1,420 megahertz. Therefore, a comet drifting through Big Ear's beam could, in principle, mimic a WoW-like tone. It's neat, tidy, and it falls apart on contact with the details. The particular comets suggested years later weren't actually in the right place at the right time. Even if they had been, their hydrogen environments don't produce the kind of sharp, needle-thin tone we're talking about. You would expect broader, weaker structure, not a narrow spike that rises and falls with textbook symmetry in a single horn and then vanishes in the second. In other words, wrong sky, wrong shape. The hypothesis was tested and found wanting. What about hydrogen itself acting like a Lazara maser in radio terms? Here the story gets more interesting. Under special conditions, a cold hydrogen cloud can tip into a population inversion where stimulated emission sharpens and brightens the 21-centimeter line. That buys you narrowness and brightness stew of our 3 demands. Could a transient trigger, say, a flare or shock, wave briefly, pump a cloud, and make it sing, WoW style? Recent work reassessing archival data suggests that narrow, enhanced hydrogen features do turn up near the line, though they're weaker and a tad wider than the 1,977 spike. If something like a sudden hydrogen maser flare exists, it would be a genuine astrophysical phenomenon worth a chapter of its own. The sticking point is getting all 3 requirements at once: razor, thin bandwidth, clean drift, scan shape, and extreme brevity without fine-tuning temperatures, velocities, and geometry into a coincidence pile. Magnetars and other exotic compact objects are the next stop. They already explain another once mysterious radio class: fast radio bursts. FRBs are brilliant, millisecond-long, broadband slashes wildly different beasts from a quiet, stable, hertz-wide tone. Could a magnetar or neutron star environment somehow imprint a narrow carrier on top of chaos? It's not the usual behavior. You can imagine plasma processes that pick out preferred frequencies, but keeping a tone crystal steady across a minute while staying needle thin asks for an engine we haven't seen in those systems. If magnetars are responsible, they would be doing something qualitatively new at 1,420 megahertz possible, but not yet observed. Interstellar scintillation. The radio twinkling caused by turbulent plasma can act like a flickering lens. It magnifies, demagnifies, and occasionally focuses background signals. Could it take a broad, modest hydrogen line and brighten a hair-thin slice of it just long enough for Big Ear to catch? Scintillation can boost and sharpen, yes. But making a truly narrow spike in a single channel for a single minute, while preserving that clean, symmetric drift profile, strains what lensing usually does. It's a maybe that needs modeling, not a ready-made answer. Consider shock in a cloud scenarios. A flare from a star or a passing blast, wave slams into a cold hydrogen patch, briefly stimulating emission exactly at the 21 centimeter line. Brevity check. Brightness maybe. Narrowness again the problem. The random motions inside even a calm cloud smear frequency. Turbulence and magnetic fields widen it further. A truly sharp line asks for a remarkably quiescent column and a very particular line-of-sight velocity field. Not impossible, just constraining. There's also the plain vanilla hydrogen line itself. The Milky Way glows in 21 centimeter light. We map its spiral arms with that emission, but that glow is broad in frequency and spread across the sky. If the wow spike were simply the galaxy being the galaxy, you'd expect a smear, not a spike, and you'd see it again. You don't. So if we score these natural ideas against the wow printout's 4 pillars narrow band, clean drift profile, proximity to 1,420 megahertz, non-repetition on wins cleanly. Comets miss on geometry and signal shape. Scintillation and shocks can help with brightness and timing, but struggle to get needles from hay. Magnetar-style engines wow us at broadband fireworks, not sustained carrier tones. Hydrogen maser flares are the most intriguing. They attack narrowness and brightness head-on, and some recent analyses argue that special conditions might exist, but the case is circumstantial. To clinch it, we'd need to catch one in the act a wow-like spike with polarization, drift, and spatial context that points straight at a well-characterized cloud, not at a star. There's a meta lesson here. Natural hypotheses should predict families, not loners. If comets can do this, there should be many near wow spikes when comets cross beams near 1,420 megahertz. If maser flares do it, we should catalog multiple events with shared fingerprints, similar bandwidths, polarization behavior, sky environments. If scintillation is the culprit, statistics should reveal a predictable rate of 1-minute spikes in certain sightlines. The way out of argument is population. The way out of what if is a list. Modern pipelines can build that list. They sit on the hydrogen line often, carve it into subhertz channels, and archive baseband voltages so that potential maser flares or anything else masquerading as a wow can be replayed and dissected. They also pair spectra with catalogs. If a spike appears, software can instantly tell you whether a known cold cloud, an HI filament, or an unusual star sits under the beam. If the spike repeats, or even if lookalikes pop up in similar environments, the scales tip toward a natural class. And if the sky keeps refusing to cooperatino repeats, no cousins, no pattern, then the most conservative natural stories get weaker with time. That doesn't make the artificial option true. It makes it resilient. It stays on the table because the sky keeps saying, not that, not that, not that, without ever showing us what it is. The most honest place to stand, 47 years on, is with 2 doors open. Behind one lies a hydrogen trick-stimulated, sharpened, and briefly lit by an astrophysical nudge we have yet to catch in the act. Behind the other lies engineering an intentional or unintentional carrier, beautifully parked near a universal landmark, sweeping across our beam once and gone. Good science pushes on both doors. It writes observing proposals tuned to each, designs classifiers that won't throw away either, and builds alerts that can summon another dish to bear witness while the tone is still alive. If a natural door opens, we get a gift, a new, rare kind of hydrogen behavior that would have hid in old analog systems but can be pinned down now. If the engineering door opens, we get something larger than a gift, we get company. Either way, WOW stops being a story about a strip of paper and becomes a story about a class of events we can test, track, and finally, explain. Treat the artificial hypothesis as engineering, not fantasy. Suppose a distant civilization wants to be findable without wasting power. What would they build? 3 options make sense. First, a beacon, a narrow, stable carrier placed where any beginner will look. Second, leakage, unintended by products of communications or navigation that bleed into space. Third, a scanning lighthouse, a high-gain beam that sweeps the sky on a schedule, illuminating each direction briefly before moving on. Why put a tone near the hydrogen line? Because physics makes that frequency obvious to everyone. Neutral hydrogen marks 1.42 GHz on the cosmic dial. Hydroxyl lines sit nearby. Between them is a relatively quiet spectral lane nicknamed the water hole. You do not need our languages or culture to choose it. In game theory terms, it is a Schelling point, a meeting place both sides can guess without coordination. If you wanted strangers to notice you across light years, you would camp beside the loudest universal landmark on the dial. How bright must a beacon be? Not as brutal as broadcast everywhere, all the time. Beaming wins. A high-gain transmitter that paints a pencil-thin spot on the sky can reach hundreds of light years with power levels humans already manage, especially if the signal sits in about a hertz. With a narrow beam, cost scales with how often you revisit a direction, not with how many stars exist. That economics favors a patient sweep. Each patch gets a brief hello, then waits its turn. That patience explains non-repetition. We listened again, but not necessarily at the right seconds. If a beam's revisit time is months or years, or if its spot is so small that Earth must sit inside a tiny crosshair, the chance of catching a second pass is low unless you watch nearly all the time. The tone could also be periodic, but tied to a long cycle-slow rotation of a transmitter, or a catalog the system marches through on a clock we have not guessed. A one-time salute is unlikely. A slow lighthouse that eventually returns is more plausible. If it was a beacon, why no message? A plain, stable carrier is the handshake. First, you let the other side notice you. Then you add structure. Modulation might be present but subtle. Slow on, off-keying, faint sidebands, or micro drifts encoding a counting pattern. Big Ear's printout discarded exactly the information you would inspect for nuance. Modern systems keep raw voltages so analysts can zoom in and test whether a plain tone hides deliberate structure. What about leakage rather than intent? Every radio technology throws off telltale carriers clocks, pilot tones, and reference beacons. On Earth, those lines are narrow and crystal stable. If a civilization runs a power grid, a deep space network, or navigation aids, some carriers could leak into space. The catch is placement. Engineering convenience and local regulation pick frequencies. They do not steer you to the hydrogen line. A leakage tone parked exactly there would be a coincidence, not a necessity. There is a third artificial path: astronomy. Imagine an interstellar radar probing exoplanets or mapping debris belts. Planetary radars use narrow, high-power carriers, often with coded phase or frequency modulation. If a civilization ran such a system in or near the hydrogen band 4 calibration, protection from interference, or tradition an Earth-pointing side lobe could brush us once as the instrument slewed, we would see a steady, narrow tone for about the minute our beam needs to sweep across the source. Then there is frequency drift. A smart beacon might include a gentle, constant drift to say, "I am on a rotating planet," or it might cancel its Doppler to hold the tone rock steady in the barycentric frame. Either choice leaves a signature. Measure it, and you can infer whether the transmitter sits on a spinning world, a free-flying platform, or a tidally locked base. Big Ear could not save the raw waveforms needed for that test. Modern receivers can. Skeptics ask, if they wanted to be found, why not shout with a broadband, unmistakable message? Because narrowband punches above its weight. It is easiest to see against noise, simplest to keep coherent across light years, and cheapest per bit. A civilization that expects beginners to do the same calculus might pick a narrow carrier at an obvious place on the dial, scarcely modulated, sweeping the sky for ages. Caution matters, too. Broadcasting a rich message paints a target on your location and your sophistication. A minimalist carrier reveals almost nothing beyond, "We exist, we know physics." If prudence or politics matters, the quiet, patient lighthouse is a compromise, discoverable without oversharing. What would confirm an artificial origin beyond simple repetition? Start with a measured, consistent Doppler drift that fits a plausible rotation or orbit. Add sidebands or faint subcarriers in rational ratios. Find harmonics at exact multiples, as if produced by known oscillators. See the same tone at two sites oceans apart, with matched timing and sky-fixed behavior. Watch polarization hold steady. Finally, catch a schedule, the same star field lighting up after an integer number of days or weeks. Alone, each is modest. Together, they cross the line from curiosity to case. Until then, the artificial door stays ajar because it is internally consistent. It explains the narrowness, the location on the dial, the beam crossing shape, and the single pass without demanding magical power budgets. It also sets an observing goal. Linger on likely shelling points with instruments that keep everything phase, polarization, and raw voltages, so the next candidate can be interrogated in full. If the wow minute was a handshake, the reply is not a poem, it is a plan. Be there, be ready, and measure every hertz. Call it the paradox of listening in a noisy century. The wow minute happened in 1977 when the radio sky was quieter and the satellite belt was sparse. Today, the heavens hum with constellations and downlinks, radar fences, and broadband splatter. We built miracles that talk to each other across the planet and then asked our telescopes to hear a whisper at the same time. That is why modern technosignature hunting looks a bit like forensic audio. You filter the scene, compare versions, cross-examine every artifact, and only then decide whether the tone in your headphones belongs to the sky or to us. That discipline begins with a quiet correction Big Ear did not apply: the sky's clock. Search pipelines now shift the data into the solar system's barycentric frame, the one point that barely jiggles as the planets dance. In that frame, a truly distant transmitter stays almost steady except for motions in its own neighborhood. If a tone is rock solid only in the observatory's local frame, odds are it is ours. If it becomes cleaner when transformed to the barycentric frame, it earns the next round of tests. Next comes drift. A transmitter on a rotating planet or in orbit will walk up or down the dial by tiny amounts. The pattern matters. Spin adds a daily wiggle. Orbit adds a slower one. Engineers can cancel that drift, but that cancellation is itself a fingerprint. It requires knowledge of celestial mechanics and a clock stable enough to hold phase for minutes. Nature can mimic many things. It rarely mimics a patient engineer. So modern backends brute force the problem testing. Thousands of minute drift rates, forward and backward, and watch which rate makes a candidate snap into focus. But spectrum behavior alone is not enough. The ground is full of chameleons. Spread spectrum links can masquerade as narrow tones when they leak through oscillators. Intermodulation, the mixing of strong signals in metal or silicon, creates ghost carriers that appear where nobody actually transmitted. Even clock harmonics from digital electronics can march across bands in crisp, tempting ladders. You learn to distrust pretty spectrograms until a second telescope, a long way away, sees the same thing at the same sky position. So the field adopted rituals that make romance difficult. On-off pointing cycles are the simplest. Stare at the candidate, nod to a nearby blank patch, then back again. A real celestial tone obeys the stars. A local nuisance obeys the hardware or the horizon. Multi-beam arrays raise the bar by watching the target and several adjacent patches at once. If the spike appears in every beam, you shrug and move on. If it lights only the beams centered on a star, you keep digging. The fastest safety check is a call across continents. Another observatory points now. Coincidence in time and sky position is the solvent that washes away wishful thinking. Even the hardware is skeptical by design. Receivers carry dual polarizations, so a candidate's handedness can be tracked through time. Backends keep rolling buffers of raw voltages. When a threshold is crossed, they dump those buffers so the first seconds are never lost. Atomic clocks, discipline oscillators, GPS and star cameras pin pointing to arcseconds. A 1 Hz wide tone can be measured to a fraction of a hertz, and a drift of a few hertz per minute can be separated cleanly from ordinary wander. That is the difference between a story and a measurement. Why does all this matter in a tale about 1 minute from 1977? Because the only honest way to honor that moment is to build a world where the next one cannot slip through our fingers. The Reading Circle taught humility. A single detection changes nothing by itself. The antidote is redundancy. Multiple beams, multiple sites, multiple times. Keep the voltages. Keep the context. Build systems that assume the first explanation is wrong and work hard to prove it. There is also a practical reality. The air above our heads grows busier every month. Constellations add thousands of transmitters. Radar fences sweep from horizon to horizon. Aircraft and ships carry radios that were rare in the 70s. It is fashionable to complain about clutter. It is wiser to map it. The most effective searches maintain living atlases of the local spectrum catalogs of satellite ephemerides, downlink plans, radar schedules, and known chirps so that when a spike appears, software can answer within seconds whether we have simply caught a passing system in a side lobe. Against that noisy backdrop, a true technosignature would look unusually disciplined. It would keep its needle-thin shape as you change resolution. It would hold phase coherently when you integrate. It would drift in a way that makes sense in a barycentric frame. If it repeats, it would do so on a schedule with a story rotation, orbit, or a scanning pattern you can predict and then verify. The longer you track it, the more it behaves like a machine, and the less it looks like weather. There is one more ingredient that 1977 lacked: openness. Many teams now publish baseband snippets around interesting events and invite outsiders to attack them. The point is not crowdsourced discovery for its own sake. It is to create healthy pressure. If a candidate survives hundreds of curious minds with different tools and biases, it earns a credibility no single lab can grant. The internet can sow confusion. Used carefully, it can also harden ideas against wishful thinking. Put all of that together, and the shape of risk and reward changes. The world is louder than ever, yet our ears are sharper and our habits stricter. The cost of a false positive is lower because we can demolish it quickly. The reward of a true positive is higher because we would capture it in exquisite detail. The wow minute remains a cliffhanger, but we have rehearsed the sequel. If a slender tone slides out of Sagittarius, again near that famous hydrogen landmark, rising and falling with the clean symmetry of a drift scan, we will not end with a strip of characters. We will end with a movie of the signal's life, a measured drift, a second dish nodding in agreement, and a plan to be there the next time it speaks. Open the case files of false alarms and near misses, because each one teaches us how to treat a whisper from the sky. Start with the peritons, odd chirps that haunted a southern hemisphere radio dish years after wow. They looked astronomical at first, swooping sweeps near 1.4 gigahertz that arrived at odd hours, but they turned out to be painfully human. Microwave, oven doors, popped open mid-cycle in a staff kitchen. The lesson wasn't embarrassment, it was method. Log raw voltages so you can replay the moment. Compare on, target, and off-target beams in real time. Correlate between instruments. And never trust a pretty spectrogram until it survives the dullest tests you can throw at it. Next, a cooler, more sobering story. A very narrow candidate toward a nearby star that briefly electrified the field. It wasn't at the hydrogen line, and it didn't shout. It whispered with discipline, drifting exactly the way a transmitter on a rotating world might. For a while, it felt like the dream. Then follow-up work found look-alikes at other frequencies and at times when the telescope targeted elsewhere. That was the tell. What looked sky-fixed revealed itself as an instrumental quark intermodulation inside electronics, creating ghost tones. The cure was protocol, not poetry. Stronger off, on, off cycles, tighter multi-beam checks, and automated searches for families of copycat lines that betray a local origin. Put those episodes together, and you get a philosophy. Assume interference until coincidence kills the doubt. Coincidence in multiple beams. Coincidence at multiple sites. Coincidence after shifting to the barycentric frame, the solar system rest frame where distant things barely jiggle. Coincidence in polarization and in a measured, sensible drift. Anything less is a story. Enough coincidences make a measurement. So where does that leave the wow minute? In a stronger light, oddly enough. Wow has faults we cannot repair. No raw voltages, no polarization record, no second sight, but it also has virtues most false alarms lacked. It sits beside a Schelling point on the dial. It rose and fell exactly like a source fixed on the sky, crossing a drift scan beam. It was needle thin rather than a messy smear. And 47 years of combing that field have not produced a tidy population of local, repeatable lookalikes that would let us shrug and say, just equipment. Other cases sharpen the comparison. Some radio oddities announced themselves as cosmic before careful sleuthing showed aircraft reflections, satellite sidebands, or clock harmonics up to mischief. Others truly were cosmic fast radio bursts that now trace back to highly magnetized neutron stars, and they taught us what an authentic astrophysical population looks like. Repetition in some sources. Statistical regularities you can chart. A diversity of behaviors you can classify. That is the bar. Any natural, wow explanation must clear. Not a single charismatic event, but a family. False positives also refine the checklist for a true positive. If a wow-like spike appeared today, you'd want 5 pillars under it. 1. Exclusivity. It appears only in the on-target beam, never in references or side lobes. 2. Coherence. The phase holds when you integrate, and the tone stays razor thin as you change spectral resolution. 3. Drift. Discipline. The frequency. Slope that maximizes focus is stable, plausible, and consistent with a source beyond Earth's neighborhood. 4. Parallax of trust. Another observatory, far away, sees the same tone at the same sky position. 5. Context a star or environment in that beam that makes physical sense, plus a repeat that either lasts long enough to track or returns on a schedule you can predict. There's a human rhythm to this too. The first plot that looks extraordinary always outruns the paperwork. Chat windows light up. Someone whispers, "What if?" across the control room. The discipline is to slow down without losing the moment. You trigger rolling buffers to capture the first seconds in baseband. You freeze the receiver state. You run the off-on-off cycle. You ping partner observatories with coordinates, bandwidth, and a provisional drift rate. You paste in the latest satellite ephemerides and radar schedules so nobody has to guess about nearby clutter. You do the boring things first, because boring things are the ones that save you from fooling yourself. Meanwhile, the software fights a quieter battle on Big Ear, never faced at scale. When very strong signals land in a receiver chain, nonlinearities can mix them into sums and differences, painting phantom tones at neat arithmetic offsets. Modern pipelines auto-search for these families. If your candidate has siblings at predictable separations, it is probably an artifact. The same logic hunts for clock harmonics, the ladder of narrow lines made by digital gear. If a spike sits on a rung that walks with temperature or power supply drift, romance ends there. Another line of defense is motion on the ground. A tone that follows the telescope as it slews or grows stronger when nearby structures reflect is likely local. Arrays are particularly good at this because they can form beams that stare at the target and beams that stare at the horizon at the same time. If the spike blooms in the sky beam and the roof beam together, the story is over. Conversely, a signal that appears only where the star sits and fades when you nod even a fraction of a degree away buys the candidate another minute of attention. Noise, oddly, is your ally when you have enough of it. With long baseband captures, you can inject synthetic tones into your own data and test whether the pipelines recover them with the right drift, phase, and coherence. That Monte Carlo habit means a detection claim comes with error bars you can believe. If the software fails on planted tones that mimic your candidate, you fix the code before fixing the universe. The same discipline applies to humans. Occasional blind drills feed analysts sham candidates so the team practices skepticism under pressure. All of this folds back to wow in a simple way. The 1977 event cannot graduate from perennial mystery to measured phenomenon because the evidence is thin. But it can keep shaping our habits so the next one doesn't evaporate. It already has. The community's reflexity insistence on, off tests, multi-site checks, barycentric frames, baseband dumps, drift fitting, and artifact hunting gear wow's real legacy. The red ink circle taught us to write better in the margins. And there's a quiet comfort in the false alarms. They prove the filters work. They show that romance is defeatable by method, and that most surprises die under the same light you would shine on a true techno-signature. When the thing that refuses to die finally arrives, needle-thin, sky-fixed, coherent, confirmed, and obedient to a physical story rather than to the quirks of our gear, we'll recognize it instantly, because we've been practicing its interrogation for decades. That is how you honor a minute that could not explain itself. You build a culture that, when the sequel happens, will not need a word like wow. It will have a timestamp, a drift rate, a sky coordinate, and a schedule for tomorrow night. Point your mental camera at the hardware that is actually listening today. Start with the giants. A single dish like the Green Bank telescope can pour an entire football field's worth of collecting area into a beam so sharp it can pick out a star in a crowded field. China's 500-meter FAST collects even Murriyang ear so large that a whisper becomes a measurable thing. In the south, Parcus also called Murriyang pairs its size with backends that carve the spectrum into hair-thin slices. Then come arrays, MeerKAT 60, plus dishes in South Africa, the Allen Telescope Array in California, and pathfinders that test ideas for the coming square-kilometer array. Arrays synthesize giant virtual apertures and, crucially, form many simultaneous beams, tiling a field like honeycomb so a narrow tone cannot hide between pointings. If you cracked open their racks, you'd find the true revolution: digital backends. Field programmable gate arrays, FPGAs, and GPUs now split incoming radio noise into billions of channels and refresh those channels fast enough to paint a live waterfall of the sky. A 1 Hz wide line is no longer a rumor at the edge of a chart. It is a hairline your software can follow, pause, rewind, and compare against reference beams in real time. Rolling buffers keep raw voltages for seconds to minutes, and when a threshold trips, the system dumps those buffers so the first precious moments aren't lost to history, the way WoW's opening seconds were. How do we decide where to point? Catalogs turn targeting from art into engineering. Gaia pins down star positions and motions with exquisite accuracy. Kepler, TESS, and ground surveys tell us which stars host planets and how those planets move. A modern plan for the WoW field doesn't just stare at Sagittarius, it cherry-picks sun-like stars. Inside the dual-position footprints, ranks them by distance and crowding, and schedules long dwells when Earth's own radio noise is quietest, and the target's velocity relative to us keeps Doppler drift tame. If a planet there transits, teams might time observations at particular orbital phases on the off chance a transmitter sits on a rotating world that beams when a certain face points our way. Search strategies learn to diversify. Some hours camp on the hydrogen water hole. Others sweep adjacent bands where engineering convenience might park carriers or harmonics. Some hunts chase leakage the unintentional carriers from power, navigation, or deep space networks that could waft off a distant world. Others prefer shelling point, beacons, plain, disciplined tones on frequencies any beginner could guess. Either way, the pipelines are agnostic about intention. They care about shapes, narrow, stable, coherent lines that survive the dullest checks. Data scale changed the culture. Petabytes of baseband and spectra do not fit in a desk drawer. They live on servers where coordinate nostalgiados the remembering. That enables something Big Ear never had: forensic reanalysis. When a near miss shows up an intriguing, narrow tone that flared for a minute, analysts can recompute its drift in the barycentric frame, rotate polarization, try alternative channelizations, and even inject fake tones into the same voltage stream to make sure the pipeline that found it would also have found a real one. The result is not just a verdict on a single candidate, it is a calibrated sense of how often the system would miss or mistake a WoW-level event. Coordination widened the aperture. Technosignature searches now piggyback on mainstream astronomy most of the time. Commensal modeso. The sky is under casual surveillance even when nobody has a dedicated SETI proposal that night. When something odd appears, an alert can hop hemispheres in minutes. Another dish spins, another backend starts rolling, and within the hour, you have 2 independent looks. That habit multi-site coincidence as a first principle matures the field beyond wishful thinking. There's a practical human layer, too. In modern control rooms, the chat pane is as important as the console. A potential candidate triggers a well-rehearsed checklist: freeze the receiver state, run the on, off, nod sequence, query satellite ephemerides and air traffic databases. De-chirp across a grid of tiny slopes. Check for artifact families at arithmetic offsets that betray intermodulation. If the line survives the grind and only then grows prettier as the analysis gets stricter, excitement is allowed to spread. What about openness? The discipline of not fooling ourselves gets stronger when strangers are invited to try. Many teams publish snippets of baseband around interesting events and welcome outside code. Citizen scientists comb waterfall plots, often with better patience than professionals sprinting between tasks. If a candidate turns out to be a clock harmonic or a satellite sideband, the correction travels fast. If it survives, it accrues a credibility no single lab can manufacture. Now cast that machinery onto the WOW field itself. Two overlapping circles in Sagittarius become a grid of microbeams updated many times per second. Every beam has a twin off-source beam watching nearby empty sky. Any spike that floods both is tossed. The back end keeps a minutes-long ring buffer. If a hairline appears near 1,420 MHz, the buffer dumps, capturing the first light. A drift fit in the barycentric frame either sharpens the line, good, or smears it, bad. A polarization trace either stays disciplined, good, or jitters, bad. Within minutes, a partner observatory in the opposite hemisphere, under a different radio environment, joins the interrogation. If nothing appears after months, that silence isn't a shrug, it's a constraint. You can turn hours on target into limits. No continuously broadcasting. 1 Hertz beacon brighter than X Jansky's in the WOW footprints. If a lighthouse sweeps, its duty cycle is below Y%. If natural hydrogen tricks exist there, they either avoid the exact waterhole frequencies you covered, or they are rarer than your cadence could catch. Those numbers tighten every season, and they're portable. The same pipelines watch other Schelling point fields, compounding the odds that if a family of WOW-like events exists, it will eventually trip over our habits. This is the quiet way the mystery moves forward. We do not relive 1977. We outgrow it. The kid in our racks can see a needle that Big Ear would have printed as a blur. Our protocols assume we are wrong and force a second telescope to disagree. Our catalogs point us to stars that did not even have names in Jerry Ehman's era. And our storage remembers everything. So if fate offers another minute of narrowband strangeness, the sequel will not be a red circle in the margin. It will be a full dossier. Rewind to the night itself and walk the timeline like an investigator. Big Ear at Ohio State was in drift scan mode. 2 slightly offset feeds waited while the sky slid past at the rate set by Earth's rotation. The back end summed power in narrow channels, then printed a row of characters for each short integration. No flashing lights, no otherworldly beeps, just the steady clatter of a line printer turning radio noise into alphanumerics. That August evening, one row jumped, where the background usually crept along as small digits, a run of letters, rows 6 EQUJ5 in Big Ear shorthand. Letters meant strength. The sequence itself meant a crest in the middle, a neat, symmetric swell as a source drifted into the beam, peaked, and faded away. Minutes later, the second feed scanned the same lane of sky and saw nothing. 1 horn, 1 pass, 1 minute. That geometry is what minted a mystery. The paper trail after that is meticulous and maddening. Observers logged the frequency channel, its offset from the famous 1,420 MHz hydrogen line, and the sidereal time when the horn was illuminated. Because the 2 feeds were separated on the sky, the geometry yields 2 possible celestial positions, almost identical in right ascension, slightly displaced in declination. Both sit in Sagittarius, a busy neighborhood near the Milky Way's plain where gas clouds, newborn stars, and ordinary suns crowd the field. Teams went back. Some listened for hours at a stretch. Others returned night after night. They widened bandwidths in case the tone wandered and narrowed channel spacing to catch a hair-thin line. They covered both candidate positions and the gap between them. They heard the ordinary radio sky galactic hiss, passing satellites, occasional interference, but never that tidy drift signature again. The WOW minute refused to repeat. 2 facts made the autopsy harder. First, the system did not keep raw voltages, only summed power. There was no way to replay the moment at finer resolution. check for subhertz structure, rotate polarization, or measure a clean Doppler slope. Second, the instrument was idiosyncratic and, years later, gone. You cannot resurrect a vanished telescope to test whether a quirky dance between analog filters and local hardware might have printed a false tone. You live with the data you have. That forced a culture of restraint. Jerry Ehman, the volunteer who circled the printout and wrote, "Wow," was cautious from the start. He cataloged possibilities, from terrestrial reflections to instrumental oddities, and resisted premature conclusions. The caution stuck. When later claims surfaced comets, exotic plasma tricks, even statistical flukes, they were tested against the few stubborn features preserved on paper: narrow bandwidth, asymmetric drift, scan shape, proximity to the hydrogen line, and single horn detection. Most proposals solve one or two of those and stumble on the rest. There's a human texture to the night that rarely makes it into equations. Volunteers kept the system running on a shoestring. The instrument was a patchwork of aluminum panels and ingenuity. Data were messy until a person poured coffee, flipped through the stack, and trained an eye to spot anomalies. The red ink wow is not a verdict. It is a heartbeat surprise, curiosity, someone catching himself being human for a second before getting back to the grind of elimination. Think, too, about the frequency. The 21-centimeter line is not a single, infinitely sharp note in the living sky. Motions smear it. Receivers choose practical channel widths. Local oscillators wander. A candidate that sits near 1,420 megahertz can honor the spirit of a hydrogen line search without landing on the exact textbook value. That nuance matters because critiques sometimes hinge on offsets of tens or hundreds of hertz, as if purity alone proved intent. In modern pipelines, such offsets are raw material. You fit them, ask whether they match a plausible Doppler drift, transform to the solar system barycenter, and decide whether the behavior feels celestial or homegrown. Now zoom out to consequence. The minute itself changed no laws of physics, but it altered habits. It nudged SETI away from one-off hero observations toward persistent, commensal listening. It encouraged archivism, keep baseband, not just power. It turned multi-site, or it didn't happen, from aspiration into reflex. And it reminded everyone that the best mysteries are the ones that survive enthusiasm and still deserve patience decades later. If you could replay the night with today's gear, you would not just hear a spike, you would catch a portrait. A live waterfall would show the hairline appear. Rolling buffers would freeze raw voltages. Dual polarizations would track handedness. On-off beams would flip automatically. A partner dish, an ocean away, would pivot within minutes. Catalog overlays would label likely stars in the footprint. You might still end without a poem, but you would end with numbers. Drift in hertz per minute, polarization fraction, a sky position with arc-minute precision, and coherence that either tightened as you integrated or fell apart as artifacts. Numbers that separate romance from measurement. There's an irony worth savoring. A single line of type gave us an outsized legend. The same scarcity of detail that makes the story romantic is exactly what keeps it unresolved. Romance thrives on absence. Science chafes at it. The way forward is not to relitigate 1977 forever, but to ensure the next anomaly leaves no oxygen for myth. When a candidate earns a circle in the margin today, the circle comes with a dataset big enough that the word beside it does not have to be wow. It can be a drift rate, a coordinate, and a schedule for tomorrow night. So the night remains a hinge between an analog era that printed characters on paper and a digital era that records the sky in exhaustive detail. 1 minute sits between them like a bookmark. Turn the page, and the rest of this story is about what our bigger ears and better habits are doing now, in those same patches of Sagittarius and across a million others. Step outside radio for a minute and look at the wider idea behind technosignatures. The wow signal is a narrow tone near a famous line, but the bigger question is simpler. If technology exists elsewhere, what side effects would it leave on the universe? Radio is one, not the only one. The sensible approach is to hunt in families and let different bands cross-check one another. Start with light. A civilization that wants to be noticed could fire nanosecond laser pulses at nearby stars. Those pulses are the optical cousin of a 1 Hz radio line, bright, brief, and easy to separate from natural starlight if you watch with fast detectors. Pick a Schelling point, an obvious wavelength tied to atomic physics, and send the cleanest, most unmistakable pulse you can. Several observatories already run pulse search programs on sun-like stars. Infrared offers another lane. Technology leaks heat. A planet-scale industry radiates waste energy, and physics says most of it glows in the mid-infrared. Surveys compare a star's visible brightness to any warm excess around it. Too much excess, shaped the wrong way, becomes a flag. But if a vetted sample still leaves outliers, you ask whether something deliberate is adding heat in a pattern dust cannot mimic, and you design follow-ups that test that idea without drama. Atmospheres carry signatures, too. Our own air contains gases that were scarce before industrial molecules with lifetimes long enough to accumulate, but short enough that geology alone would not make much. Seen from far away during a transit, Earth would show oxygen, a whiff of methane out of balance with that oxygen, and industrial molecules at tiny levels. The point is not to hang hope on a single gas. It is to stack clues until the odds favor technology over geology or biology. Now ask the hard statistical question: what does non-repetition do to belief? 1 minute in 1,977 is not much data, and a Bayesian would say your prior matters. If your prior for distant transmitters exist and point at us sometimes is very low, one lonely spike barely nudges you. If you start agnostic, the posterior moves a little but not far. The evidence is thin and the space of mundane explanations is large. The way to change that is not by arguing louder. It is by collecting more minutes with better instruments. Time budgets enter here. If a beacon sweeps slowly, the chance that we happen to sit in the beam for that 1 minute is small, yet not absurd. The remedy is patience measured in years. Commensal searches help. You listen while doing other science, stacking thousands of hours without bankrupting a telescope's calendar. Over 5 or 10 years, the "we just missed it" excuse shrinks. Either a scanning lighthouse comes back on a schedule you can catch, or it does not. There is a quieter route to closure: populations. We learn this with other cosmic surprises. Fast radio bursts looked like fireworks at first. Then repetition and patterns tied many to highly magnetized neutron stars. If there is a natural wow effect, say, rare hydrogen line flares sharpened by calm cloud sweep should see cousins under similar conditions. The absence of a population does not prove intent, but it weakens nature's case and pushes us to look harder or look elsewhere. Culture rides shotgun on all of this. Wow became an icon not only for what it was, but when it happened. The 70s had fewer satellites, a gentler radio horizon, and a romantic idea of first contact that modern noise and discipline have sanded down. Today the field wears a lab coat. Proposals quote duty cycles and false alarm rates. Pipelines publish their code. Candidates arrive with data anyone can download and dissect. Back to practice. If you were crafting a campaign to revisit the wow field with today's toolbox, you would split your bet. Radio would cover the waterhole and its shoulders with subhertz channels and precise drift tracking. Optical stations would keep watch for nanosecond pulses from solar analogs in the same footprint. Infrared surveys would check for warm excesses that dust cannot explain. Spectrographs would time their stares to planetary phases for a short list of stars. None of these alone proves anything. Together, they create a triangulation problem a real signal can solve. Even negative results do work. If radio stays quiet for thousands of hours, you turn that into a bound on how often a wow-bright beacon could sweep past without being seen. If optical arrays never catch a pulse above set thresholds, you limit how often a nearby civilization could be pinging your neighborhood. If infrared samples show no peculiar excess among candidate stars, you favor dust over industry. Progress can be a stack of no's that fences off the landscape where a yes would have to live. Where does that leave the mystery emotionally? Still compelling, but smaller in the best way. Awe is not a plan. Curiosity is. The red ink circle did its job by waking up a generation of careful listeners. The sequel is not a dramatic reveal. It is a patient audit of the sky with instruments that refuse to be charmed. If a second wow happens, it should bring friends, polarization curves, drift fits, multi-site stamps, and maybe neighbors in other bands. If it never happens, we still win by learning what the universe refuses to be. A final note for storytellers and engineers alike. Do not promise fireworks, promise a ledger. The ledger is how mysteries end, not with one spectacular line, but with many small entries that add up to certainty. The wow minute was one entry. Since then, we have built bigger ears, better habits, and sharper humility. Keep writing. The universe is patient, and we can be, too. Imagine the next minute isn't a one-off. A narrow tone rises near the hydrogen line from the wow field, and this time we catch it with modern gear. What happens between the first whisper and the first press conference? There's a quiet protocol, half culture, half habit, that turns a jolt of adrenaline into a measured case. Minute 1. Capture everything. Rolling buffers, dump raw voltages, so the opening seconds are preserved. The system locks its frequency standard, logs receiver state, and stamps the time in both observatory and barycentric frames. On-off beams run in a tight loop to prove exclusivity. The tone must appear only where the star sits, not in reference beams. Minutes 2 to 10. Call a friend. A partner observatory, far away and under a different spectrum, slews onto the same coordinates. If they see the same tone with a consistent drift in the barycentric frame, interference falls away. If they don't, you keep listening, but keep your excitement to yourself. Coincidence is the solvent. Without it, stories cling. The first hour, anatomy. Analysts fit the frequency drift. Does a single slope sharpen the line, or does the tone grow fuzzier as you de-chirp? They test polarization stability. They rechannelize the voltages at finer resolution to search for faint sidebands or harmonic telltale fingerprints of oscillators or modulation. They fold the data on plausible periods. A rotating transmitter might wobble the tone in a pattern that repeats. At the same time, software cross-checks, satellite catalogs, radar schedules, and aviation databases. You'd be amazed how many romantic plots die in that hour. The first day, no proclamations, just repetition. The target zone gets scheduled again and again, at different times and Doppler geometries. If the tone persists or reappears on a schedule you can predict, your confidence climbs from interesting to compelling. If it vanishes for good, your paper will be careful, not triumphant. Wow taught that discipline. Only then do you talk publicly, and when you do, the release isn't a manifesto. It's a data drop, baseband snippets, drift fits, beam maps, polarization traces, and a list of all the ways you tried to kill the signal and failed. The point isn't to win the internet, it's to invite attack and survive it. If a case collapses, better fast and loud than slow and quiet. Now imagine it is real and steady long enough to study. What could we learn from a tone that carries no obvious message? More than you think. Information lives in structure. A truly artificial carrier will often be too perfect. Its coherence beats thermal noise. Its phase holds over long integrations. Its drift rate makes physical sense. Even in a minimalist beacon, subtle choices leak clues. A tiny, constant drift might encode a rotation rate. A faint pair of sidebands set at rational offsets could be calibration marks. Here is our clock. Polarization that stays fixed while crossing the beam implies an engineered antenna. A rotation of polarization with a stable period hints at a spinning emitter. Engineers would try gentle provocation, observing at harmonics and subharmonics, widening the band to look for a hidden data channel near the carrier, and watching for time division behavior brief intervals where the tone changes state in a pattern that repeats with prime number gaps or other mathy motifs. A narrow beacon is the handshake. The message, if they ever send one, likely lives on a nearby channel where more bandwidth buys more bits. That leads to a sober expectation check about decoding. A 1 Hz wide line with high signal to noise is excellent for being found. It is terrible for fast communication. To keep a 1 Hz tone clean across light years, you integrate slowly. Slow integration kills data rate. If the other side wants us to actually read content, they'll either drift the carrier through a deliberate pattern we can accumulate over hours, or they'll switch to a wider, brighter channel after the handshake. Decoding might look less like Hollywood and more like patient, low bitrate telemetry, simple modulations, heavy redundancy, and enough repetition to survive cosmic static. Suppose there is content. How would we even recognize it? Start with Shannon, not poetry. Does the sequence of on-off changes have a complexity that's neither pure noise nor trivial repetition? Does compressing it reduce its size predictably? Do symbol timings settle into a small set of values as if drawn from a clock? Does the spectrum show the tidy skirts of a known modulation frequency shift keying, phase shift keying, or a primitive spread spectrum? Even a few consistent features shift a signal from weird to engineered. The first aha might be boring. A plot where energy clusters at rational ratios, or a histogram where symbol lengths fall into neat buckets. Boring is beautiful when you're trying to prove intent. Who speaks for Earth if it is real? That argument is older than WoW. Some say don't transmit, METI, without broad consent. Others say we've been radiating for a century and the horse has left the barn. The wise stance, at least in the first weeks, is listening only. Confirmation is fragile. Announcing a reply too soon tempts spectacle over science. The first duty is characterization, not conversation. There is also the decode trap. Humans are pattern machines. Give us static and we will find faces. That is why blind analysis matters. Split the data so independent teams try to extract structure without conferring. Pre-register the tests you'll run, and publish the negative attempts along with any promising ones. If the tone hides arithmetic, geometry, or physics primers, you want the evidence to look like a controlled study, not a Rorschach test. Now return to the older question. What after 47 years do we still genuinely not know about the WoW minute? 4 holes remain. 1. Exact frequency behavior. Without voltages, we don't know if a tiny Doppler slope was present. 2. Polarization. We don't know whether the tone had a fixed-handedness that would have screamed antenna. 3. Precise sky position. The dual horns left 2 nearby patches. We still don't know which lane hosted the source. 4. Population. We have not found a family of look-alikes in similar environments, either natural cousins that would vindicate an astrophysical mechanism or artificial siblings that would tie to a scanning beacon. And yet, those holes are not failures. They're a to-do list. Modern campaigns can measure each missing piece in minutes if the sky ever offers a repeat. That is the quiet triumph hidden inside a mystery that refuses to resolve. It forced us to build habits and hardware that won't let the next one get away. So if a second wow rises tomorrow needle thin, near 1,420 megahertz, drifting just so as Earth turns, we know the play. Capture, compare, confirm, characterize. Only then, perhaps, consider conversation. The legend began with one word, written in red. The conclusion, if we ever earn it, will be written in numbers. Look ahead a decade, and the wow question becomes less, what was that minute? And more, what can our next minutes be? The tools coming online are not just bigger dishes. They are quieter skies, longer baselines, and software that treats the spectrum like a living terrain instead of a static dial. Imagine three frontiers: place, scale, and mind, and how each changes the odds that a narrow, disciplined tone will be caught and kept. Place matters because Earth is loud. The best ears now flee to deserts, high plateaus, and protected radio-quiet reserves, where cell towers and radar fences are thin on the ground. Arrays in these sanctuaries form dozens of simultaneous beams across a field, so a spike that would once have sat between pointings now has nowhere to hide. Beyond Earth, the ultimate sanctuary waits on the far side of the moon. Shielded from our planet's sprinting cacophony, a farside station could listen through the lunar night with almost no human chatter to sift out first. Even a modest pathfinder there would demote half of today's false alarms to non-issues. Scale reshapes sensitivity. A single giant dish hears faint tones. Many dishes spread across kilometers hear fainter ones and, crucially, say exactly where they came from. Very long baselines turn phase into position, correlate a narrow line between far-flung antennas, and it snaps to a point on the sky with arc-second precision. That precision is a different kind of power. It lets you say, without romance, the tone sits on this star, not that cloud, and then schedule spectroscopy, photometry, and pulse searches on the right object the same night. Scale also means time on target. Commensal observing piggybacking technosignature scans on ordinary astronomy gives us thousands of hours almost for free. The longer you listen, the smaller the alibi for a slow lighthouse that seldom sweeps our way. Silence becomes a measurement. If a beacon revisits a patch every few months, a patient ever on campaign will either catch it or push its duty cycle into implausibility. Mind is the quiet revolution. Machine learning systems now triage torrents of events without pretending to be oracles. Unsupervised models learn the shape of normal interference and flag outliers. Supervised classifiers trained on millions of labeled glitches knock out families of clock harmonics, radar chirps, and oscillator spurs. Anomaly detectors then dump raw voltages for the handful of survivors. The human work shifts from spotting to adjudicating, less staring at waterfalls, more asking whether a line stays coherent as we integrate and whether it strengthens in the barycentric frame. There is also a frontier in architecture. We can build networks that act like one instrument. Picture a hemisphere-spanning chorus of mid-sized dishes that, when a candidate appears, lock clocks, share baseband, and synthesize a gigantic virtual aperture in minutes. Localization becomes surgical. Parallax tests become trivial. A genuine sky-fixed tone cannot hide in the weeds of local clutter when the weeds are different on 3 continents. The spectrum still has favorites. The hydrogen water hole remains the best rendezvous point, flanked by hydroxyl lines that together sketch the ingredients of water in physics rather than in language. But future frontiers add harmonics and sidebands where engineering convenience lives, and lower radio where ionized space is less forgiving, yet backgrounds can be quiet. Some teams even eye extremely high frequencies where narrow carriers can be made exquisitely stable. The principle is not to guess a single channel. It is to meet engineering halfway by watching the places an engineer would naturally choose. Think, too, about complementary messengers, optical pulses ride on cheap, fast detectors already bolted to telescopes, infrared excess surveys reuse sky maps made for dust and exoplanets. If a narrow radio tone survives triage near a sun-like star, a modest optical setup can strobe that star for nanosecond flashes the same night. Crossband choreography turns a candidate into a campaign. Now push the engineering imagination outward. Suppose a civilization parks a transmitter beyond a few hundred astronomical units and uses its star as a gravitational lens, focusing radio the way a stupendous dish would. That geometry takes kilowatts and turns them into something we could hear across a large slice of the galaxy, provided you know where to look. It sounds exotic. It is simply general relativity used as an antenna. If such tricks are common, the sky might hold pencil-thin beams that only rarely brush Earth, which makes patience the most valuable resource we have. There is a nearer version we can actually do. Put quiet ears far from our own radio smog. A small receiver, riding with a deep space probe, could listen in a cleaner environment and forward distilled candidates home. The cost is propulsion. The reward is a view of the hydrogen line without the chatter of our own planet. The farther we carry our microphones from ourselves, the less we must distrust every pretty spike. Culture evolves alongside hardware. The community now rehearses drills for candidate days, the way observatories rehearse for eclipses. The scripts are boring by design. Lock clocks, freeze states, nod on and off, call partners, fit drifts, publish small baseband windows, let strangers attack, respond with more data. By slowing the first hour down, you accelerate the verdict. Either the signal collapses quickly under pressure, or it survives long enough to deserve the kind of time no committee will deny. If all of this sounds less romantic than the red ink legend, good. Romance confuses. The future we are building makes room for awe, but not for ambiguity. The moon's quiet far side, baselines that triangulate, software that never blinks, and catalogs that turn fields into annotated maps together. They take a 1-minute riddle and set the stage where a second minute would become a measured fact rather than a story. And if that fact never arrives, the same apparatus will have fenced off a huge region of possibility and turned a question mark into a constraint we can trust. Walk into a classroom and write 6EQUJ5 on the board. You do not need to explain the letters. The room will lean forward on its own. Part of the WoW legend is narrative gravity. The characters look like a code. The red circle feels like a secret, but the enduring power of that minute lies in how it sharpened our sense of what counts as evidence, how it taught a community to trade romance for protocol without losing wonder. The first lesson is about humility in the face of thin data. We have just enough to be tempted and not enough to be sure. That combination breeds folklore in most fields. Here, it bred checklists. Successors to Big Ear wrote down the dull moves you must make before you trust an anomaly. Compare on, target, and off-target beams. Demand a second sight. Lock clocks to atomic standards. Store voltages. Measure drift in the barycentric frame. And publish what you saw quickly enough that others can attempt to break it. The list reads like a refusal to be romantic, and that is the point. The antidote to myth is not cynicism, it is method. The second lesson is about patience with uncertainty. 47 years of non-repetition are not a punchline, they are a measurement. If a lighthouse exists and swings past rarely, that rarity can be quantified. The number of hours and the sensitivity of the ears set limits on duty cycles and power budgets. Our ignorance, made precise, starts to fence the problem. The fence moves a little every year as we stack more listening time. Progress, in this domain, is often the slow tightening of a noose around the implausible. The third lesson is about how to speak in public. Most spectacular claims die in the first weekend. demolished by someone who knew a detail the excited team overlooked. The best groups now lead with caveats and with data. They say what would refute the candidate before the internet says it for them. They invite attack because science that survives attack earns trust it cannot borrow. When a team finally uses the word detection, it comes wrapped in baseband, beam maps, drift fits, and a calendar of re-observations anyone can copy. There is also a lesson about our own pattern hunger. Humans are superb at finding faces in clouds, rhythms in noise, meaning in runes. That gift becomes a trap when the data are thin. Blind analyses and pre-registered test shapits borrowed from medicine and psychology now show up in technosignature work. Teams decide in advance what tests they will run, split data so independent analysts cannot steer each other, and publish negative attempts along with anything suggestive. If a tone hides arithmetic or geometry, it should survive a skeptical gauntlet, not just a late-night hunch. A subtler lesson hides in the choice of where to listen. The waterhole is not merely tradition, it is a way to make independent searches overlap. If everyone camps near a universal landmark, a true beacon has a better chance of being caught by multiple ears. Convergence is a kind of replication. You cannot coordinate the sky, but you can coordinate your priors. The wow story also reframed the meaning of failure. Non-detections are not empty. They harden the null hypotheses you need to trust a positive. They discipline the algorithms. They produce catalogs of interference that save future nights. They even improve unrelated astronomy by pushing instruments to be calmer, cleaner, and better calibrated. In a strange way, the most useful outcome of a year of quiet listening is not disappointment. It is a sharper instrument for the next year. Zoom in on the human center of the story: a volunteer, a printer, a margin note. The image is disarmingly ordinary. That ordinariness is a gift. It reminds us that discovery often begins as boredom interrupted. It is why open archives and citizen projects matter. The eyes that catch the next minute might not belong to the person who wrote the proposal. The line between professional and amateur is thin when the data are rich and the tests are clear. Democratizing the watch does not cheapen it, it multiplies it. Now tilt the camera toward the future public moment, the day when a candidate survives the gauntlet. How do you talk about it without lighting a bonfire of speculation? You narrate what you measured, not what you hope. You show the on-off cycles, the two-side plot, the drift that looks like a planet's spin, the polarization that refuses to wobble. You say what you still do not know. You give dates for the next tries, and you invite others to try them too. You avoid the word message unless there is one. You avoid the word alien unless every dull explanation lies in pieces. There is one last lesson, and it is emotional. Awe is allowed. The discipline is to put awe after analysis, not before. A clean, needle-thin tone that wheels across a drift scan and returns on a schedule will make the hairs on your neck rise. Let them, then pick up the checklist and keep going. The red ink taught us that it is possible to feel two things at once: the thrill that something might be out there, and the responsibility to be boring until you can prove it. So the classroom board holds its 6 characters. They mean a bright, narrow spike near 1,420 megahertz that rose and fell once. They also mean build habits that will not let the next one slip. The wonder lives in both sentences, the original minute and the patient method it. Inspired, if the universe eventually answers back, the reply will not erase the need for method. It will vindicate it. Words, 950. 4. Section 16. 17. Return to the original strip one last time. A summer night. A long, low instrument, listening as the sky slides by. A handful of characters that look like a heartbeat. 6 EQ UJ 5. The red circle has faded in photographs, but the minute it marked is still doing work. It turned a hobby of hope into a program of record. It taught us to build ears that keep everything and habits that throw nothing away too soon. It made a community out of scattered experiments. And it left a sentence unfinished. If that was not noise, and we still cannot say it was, what was it? Here is the most honest answer after 47 years. We do not know. We can tell you what it looked like: narrow, bright, clean, drifting like a source fixed on the sky in a drift scan beam. We can list what it probably was: not a common comet, a broad splash of hydrogen, a messy burst masquerading as a carrier. We can show you models of what it could have been: an engineered beacon sweeping a pencil-thin spot, a rare flare in a calm hydrogen column, a reflection that managed to mimic a celestial drift. We can quantify how much power a transmitter would need at various distances if it beamed tightly, and how implausible an isotropic shout would be. We can tell you how often telescopes have returned to the field and how carefully they have failed to find a twin. But we cannot change the noun. It remains a signal, not a source. The figure lacks a face. That stubborn fact is less frustrating when you notice what the minute enabled. It pushed instruments to record baseband voltages so that the first seconds of a candidate are never again lost to summary printouts. It normalized the habit of on-off beams and multi-site checks. It encouraged catalogs that turned star fields into shopping lists for targeted stares. It nudged allied searches to bloom: optical pulses, infrared waste heat, atmospheric oddities. It made openness a virtue. Publish what you saw quickly and let the world help. The legend did not grow because a volunteer wrote "wow" in the margin. It grew because the community answered with "how" and then built tools good enough to reply. When you step back that far, the story is not really about aliens. It is about how science behaves when an answer might be out there, but the evidence is thin. You slow down. You define what would change your mind. You count the hours and publish the nulls. You admit how hard it is to hear a whisper in a city you yourself built. You learn to prefer ledgers to myths. And you keep a small, protected space in your head where awe is allowed to live, contingent on results. The practical epilogue is straightforward. The two patches of Sagittarius that Big Ear's geometry left us are no longer just circles on an old map. They are living targets. Modern arrays tile them with microbeams, single dishes, roll ring buffers, and fit drifts in real time. Partner observatories keep night watches that overlap just enough to answer a sudden call. If a narrow, disciplined tone rises there again near the waterhole, clean in polarization, sharpened by a sensible Doppler slope, we will not file it under legend. We will file it under coordinates with timestamps, confidence intervals, and a calendar of next attempts. The sequel will have numbers for a name. Maybe that sequel never comes. Maybe the wow minute was a confluence of quirks we will never reproduce. If so, the discipline it seeded remains a net win. The same ears and protocols that would have confirmed a beacon also sharpen the rest of astronomy. They make radio maps calmer, pulsar timing cleaner, planetary radar safer, and interference catalogs better. In a world that gets noisier every year, that calm is its own quiet triumph. But if the sequel does come, a hairline appears where hydrogen hums, rises, and falls with the grace of a drift scan, and returns when prediction says it should, then red ink will give way to a different color. The pale blue of a new folder on a shared server, labeled with a date and a drift rate. Inside will be voltages, beam maps, polarization curves, plots with error bars, and a short note that says only what it must. Others will download it. Tests will repeat. A schedule will fill. The minute will lengthen into a conversation measured first in cautious words, and then, maybe, in bits. We end where we began, with a printer that rattled and a volunteer who wrote a human exclamation beside a superhuman question. The question endures. The exclamation is ours to earn. To do so, we keep listening carefully, skeptically, patiently at the places the universe itself points out. If we are not alone, the path to knowing will look exactly like this, a ledger of minutes that behave like machines, sifted from a century of noise until the figure finally gets a face. If we are alone, we will have discovered that honestly, having used our best ears and our best habits to ask. Either way, a single minute from 1977 will have done its job. It taught us how to hear. That is what still cannot be explained about the wow signal, 47 years on. Not just what it was, but what it made us build in order to ask again with better ears, steadier hands, and the kind of patience that turns mysteries into measurements.